Alrighty, so it's 101. Thank you all for joining us for today's webinar, New Refrigerants in Building Design. My name is Tristan Grant. I'm an Associate Director with the Codes and Policy team here at NBI, and I'm really happy and pleased to be with you here today and help moderate this session. We'd like to thank San Diego Learn program for sponsoring this and for providing the opportunity to present this material to you. You can access their website if you're interested to find out more about what they do. I'm sure many of you are aware of the current and upcoming changes to refrigerant requirements in the US. We're going to discuss the status of those regulations, what exactly the changes mean, and some of the implications for manufacturers, designers, installers, and what this means for many high-performance buildings. As we're going along, please feel free to put questions in the chat. We'll try to answer those as we go along, and we'll have an opportunity at the end to dig in a bit more and discuss that with everyone. So now I'd like to introduce our speakers. Helen Walter-Terrinoni is the Director of Global Climate Policy at Trane Technologies. Prior to this, she worked as Vice President of Regulatory Affairs at the Air Conditioning, Heating, and Refrigeration Institute. Helen has also worked in regulatory affairs at the Chemour company and sourcing planner at DuPont. Helen holds a master's degree in chemical engineering with a concentration in environmental engineering from Syracuse University. John Milkint is the West Coast Territory Manager at Chemour. He has over 25 years of experience in the HVAC industry, including as a sales manager of HVAC equipment and control systems with Trane. He has a BS, Bachelor of Science in Mechanical Engineering from the University of Wisconsin, an MBA from the University of Toledo. He is a Midwesterner, originally from Wisconsin, who currently resides in the mountains of Southern California, and he is a minority shareholder in the Green Bay Packers and maintains a season ticket package at Lambeau Field. And Ben Burnett is an innovative mechanical engineer with a decade of experience in sustainable building projects. He has led teams of engineers, designers, and CAD specialists, and is skilled in energy modeling to guide projects towards sustainability and efficiency goals. And with that, I'd like to hand it over to them.
Mic off. Mic on.
Thank you so much for the introduction, Tristan. If you go to the next slide. So I'm going to talk a little bit about refrigerant policy, and I think probably most, if not everyone on this call, knows the history of refrigerant transitions, but I just summarized it here, and I think that you'll have access to these slides later around this history. You know, the Montreal Protocol for substances that deplete the ozone layer, or ozone depleting substances, ODS, has been in place for many decades, and we have seen the transition from chlorofluorocarbons to hydrofluorocarbons, HCFCs and CFCs, to hydrofluorocarbons, largely in the refrigerant space for air conditioning and refrigeration equipment. And now we're seeing a new transition, as agreed upon by the Kigali Amendment to the Montreal Protocol, to transition to lower global warming potential alternatives. You can go to the next slide, Tristan, thank you. So here's just the schedule that was agreed upon through the Montreal Protocol that basically is a phase down, in case you don't know, this is a little bit nuanced, of the supply of HFCs, or hydrofluorocarbons, HFCs. So that supply, it is denoted as production and consumption, and consumption just means the production plus import minus export of controlled substances. So there's a list of HFCs in the Kigali Amendment to the Montreal Protocol, and it exactly matches what is in the AIM Act, the American Innovation and Manufacturing Act, that was enacted in 2020. And we have seen EPA to kind of promulgate some regulations related to that. So this just shows the schedules in many countries, in case you're interested in those, and how that's unfolding. And now we're going to go to the next slide and talk a little bit about some U.S. specific regulations and the AIM Act. So under the AIM Act mandates that EPA phase down the supply of refrigerants, the production and consumption of HFCs, and then it authorized EPA to set global warming potential limits, so GWP limits, on a set schedule for different types of equipment and uses of HFCs. It also authorized EPA under subsection H to reduce emissions and maximize reclaiming of refrigerants. And so we have seen rules in each one of these spaces finalized and implemented from 2020 until now, with the latest being the refrigerant management rule. And we're going to talk about all of that in a minute. In case you are unaware as well, the Climate Alliance states, there are 12 of the Climate Alliance states here highlighted on the map to the right, to help us to understand that there are significant new alternative policy programs, so EPA's SNAP program rules that were adopted by these 12 states and have been in force since last year, in many cases for refrigerants, especially for chillers. And so we have seen that in place for this period of time. So I did want to pause for a little minute, and I know that there's been a lot of discussion and a lot of information in the news about the status of regulations and so on. And so I just want to pause for a minute and maybe describe what's happening there. Under the Congressional Review Act, the CRA, Congress is allowed to review and revisit regulations that were finalized in about the last 6 months of the previous administration. And the subsection H rule on refrigerant management is included in that list, and there are proposals for Congress to review that rule. There hasn't been a lot of sign-on to that proposal at this time, so we don't know that that's going to move forward, and there is a limited time span for a fast track on that decision. So more to come on that, but I didn't want to leave this slide without making mention of that, that is ongoing. So we can go to the next slide to kind of talk through some more details. So this just shows kind of the EPA's timeline and transition timing and global warming potentials for refrigerants. And you can see here some details around some of the 12 states that did enact refrigerant transition bans as well. So we've, and again, I think you're going to get these slides, so I wanted to make sure that I added a lot of detail here for you in case you have missed some of this information. So we've included here the manufacturing deadline for the 700 global warming potential or GWP limit, as well as the install and sell-through deadlines. And so there's a little bit of a nuance under EPA's technology transition TT rules under the AIM Act, in that they broke equipment up into two categories. One is products, where the refrigerant loop is closed in the factory, and the other is systems, where the refrigerant loop is closed in the field. And so they've treated those a little bit differently depending on that, where there's a system installation deadline, and then there's a 3-year sell-through period for products where the refrigerant loop has been closed in the factory. So it's a little bit nuanced, but we've tried to add as much detail here as possible. There's also a number of footnotes on the right-hand side around permit allowances and different specifications, as well as a link to some of these sources. Tristan, you can go to the next slide, and thank you so much. Here's some details from California. So I mentioned that, some of these states, so we've got 12 states with chiller rules and some commercial refrigeration requirements. And then we've got 3 states, California, Washington, and New York, who have requirements around additional requirements that are more akin to the TT rule in the AIM Act, around especially unitary and air conditioning systems, what is called under the AIM Act residential and light commercial systems. And you can see here those global warming potential limits. Instead of the 700 limit is 750. And you can see that there are some, again, nuanced footnoting in these rules. So I mentioned before for the US rules around systems and the difference between systems and products. In California, there's a requirement that if an outdoor unit, a condensing unit on a system is changed on a single condensing unit system, that it triggers the requirement for the new refrigerant. And so that's a little bit unique. There's also some permitting allowances, and those are all kind of documented here on the slide in case you have specific questions around all of the details of this rule. I think the next one, we're going to talk about New York. So in New York, the Department of Environmental Conservation, under Part 494 of their regulations, they have harmonized with the EPA SNAP rules, as well as the technology, the TT rules under the AIM Act, except for they've added another step. And I want to identify a couple of nuances here. One, where they've been required to list a global warming potential. So, for example, data centers, where they've got a January 1st, 2026 date for transition, they've listed a number here of 2690 GWP instead of the 700 GWP that I have translated from their pointing to the AIM Act TT rule. The 20-year GWP, and we're going to go into this in another slide in a minute, but does translate to approximately that 700 GWP value, so that GWP is pretty aligned with EPA, but the data is a little bit different for data centers, as noted here on the slide. Separately from that, you do see here 20-year GWP requirements with later dates. So another transition for New York is in their finalized regulation, which was published in December of 2024. And you can see again here on the right of the table some of the details, nuances that we talked about. So they adopted a similar requirement to California, where an outdoor unit or a condensing unit does trigger the requirement for lower GWP refrigerant. They also have some slightly different requirements around industrial product refrigeration, so IPR, and some extensions for permits. And that's all kind of listed on the right-hand side of this table for your reference. And then finally, I think the next slide, Tristan, is just kind of a view of just to try to help people understand what the heck this GWP 20 means. Global warming potential is basically assessed by organizations like the National Oceanic and Atmospheric Administration, so NOAA. They take some measurements and do some calculations and some modeling to determine the lifetime of a chemical in the atmosphere, and then they look at its radiative forcing or its climate impact, and that's how they have determined the global warming potential, as well as the time horizon to calculate the GWP. And you see here on the right-hand side some details here. Happy to talk offline with people if they want to get into some very detailed discussion around this. But this just kind of shows how that calculation is done. And basically, the GWP 20 is that 20-year GWP is calculated based on the 100-year, which is it's just kind of a reference to that. Separately from that, in case people don't know, GWP of carbon dioxide is 1 for the 100-year, and that is used as a reference point, and all the other GWPs are basically referenced to that number. So just a little information around this GWP 20 that New York is using, and how you can see the 2690, how for R32 is kind of listed here, and how that is a little bit different than numbers that you may be more familiar with. And with that, Tristan, I think that might be my last slide, but
Mic
we'll
on.
see.
Yeah, that looks right. So thank you so much, Helen. And I think now we're going to open it up for a quick poll question for everyone. And the question here is, which of these is a possible ignition source for R32? And we've got a toaster, an electric heater, an open flame, or a spark. And I can't tell from my end if the results are visible for everyone. They're not. Well, I'll hand it over to you, John, and you can continue on and let folks know what the answer there is.
So yeah, the correct answer is open flame out of all those options. So yeah, if we can go to my slides here. I've done a lot of presentations in front of contractors, in front of distributors, right? So I'm going to take about 2 hours worth of information and squeeze it into 14 minutes for you here now. So let's go forward another couple slides to more of these. Here we go, right here. So let's talk about the flammability. This is the number one thing that comes up when I'm in front of a group. And basically, you know, we've been tasked with driving refrigerants to lower global warming potential refrigerants because of all of those regulations that Helen just went over. Thank you, Helen, for doing that for us. When we come up with the new refrigerants, they get sent to ASHRAE for classification purposes. ASHRAE is going to classify refrigerants based upon two things: toxicity and flammability. So the scale for toxicity is pretty basic. A is less toxic, B is more toxic. For flammability, traditionally it's been 1, 2, and 3. 1's non-flammable, 2 is medium flammable, 3 is highly flammable. And the way that ASHRAE tests refrigerants for the flammability, they put them in a testing chamber. There's an ignition source, and they measure the flame of ignition, right? So when I first started doing this presentation, it was pretty alarming to me. A non-flammable class 1 refrigerant actually does ignite in the laboratory setting. But that flame propagation is measured. If that flame propagation is less than 90 degrees, that's considered to be a non-flammable refrigerant. It's not going to propagate. It's not going to continue to burn. So these new refrigerants that we developed, lower global warming potential, look like the picture on the right here, okay? And the first time I saw this, I look at that and like, that's really similar, right? It's not that flammable. But when we compare it to a 90-degree angle, that flame propagation goes just beyond 90 degrees. So by definition, ASHRAE had to call this a flammable refrigerant, but it's not that flammable. So they struggled, right? It's not a class 3, it's not even a class 2. They came up with a whole new designation, 2L, for lower flammability. That more accurately describes the flame propagation. So if you go to the next slide here, that's a class 3 refrigerant. That's a hydrocarbon, propane, isobutane. That's really flammable, okay? The problem is the fire code's black and white at the time, okay? It's either flammable or it's not flammable. So that those two pictures on the right, the class 2L, the class 3, they were both considered flammable refrigerants, fall under the exact same codes and standards by NFPA, which is the National Fire Protection Association. Meanwhile, the two refrigerants on top, even though they're very, very similar, treated completely differently by the codes and standards. So the codes and standards are being rewritten by NFPA to address levels of flammability. That's really important when we look later about storage and how we treat these refrigerants. So next, I want to show you a video of actually trying to ignite this refrigerant. And this is a great video. I found it on YouTube. It's a professor in Australia. In fact, I even asked my marketing department, can we make a professional video like this? And they said, well, in order to do that, we have to illegally release refrigerant into the environment, try to ignite it. We're going to film that and we're going to show people. So I got a hard no, but luckily this is out on YouTube for us to see. So if you can go ahead and play this.
Our ignition source, a carbon refrigerant, which is a class A3 highly flammable refrigerant. Okay, the first stage of the demonstration will be to see if we can ignite R1234YF, or A2L refrigerant. So we will just gently open our cylinder, face our torch away from the cylinder, open our blowtorch tap. We've got nice flow of refrigerant coming out of the end of the torch. And I've just got a common flint ignition source, commonly found in all workshops, and you can't see really any flame propagating there at all. You can if you look closely, there is a very, very mild ignition occurring in the back of the torch there, but not every time. But certainly it will not support a decent flame. As If I increase the velocity, I've still got nothing. So as you can see, the class A2L will not ignite at all.
All right, that's good right there. We can stop that. So I do want to make a couple comments. You know, it's difficult to ignite the A2L refrigerants. You've got to have ideal conditions. When they do actually ignite, I tell people not only can you outrun the flame, you can outwalk the flame, and it's going to flame out fairly quickly. So I try to put contractors at ease when I talk to them about, you know, if they're installing systems for their customers, whether it's light commercial, whether it's residential homeowners, you know, and there's concern about the flammability of an A2L refrigerant. The equivalency of flammability for an A2L refrigerant is the same as olive oil, right? People aren't scared of having olive oil in their home. I've got it right next to my gas burning stove, so it's not something that concerns me. So, but out of an abundance of caution, we are taking the flammability very seriously. The OEMs that are manufacturing equipment, they're including refrigerant sensors so that you can tell if there's a refrigerant leak with an A2L, and then that's going to be tied into the control panel. There'll be a leak mitigation strategy. So, you know, we want to make sure we're using A2L refrigerants that are mildly flammable in the safest manner possible. The OEMs, the equipment manufacturers, they're going to have details on, you know, where those sensors go, what their leak mitigation strategies, and it could be different depending upon who the manufacturer is. So moving on here, I like to tell people about the different air conditioning refrigerants that are available. I'm not going to focus on low temp, medium temp refrigeration, just the air conditioning in this session today. And if we go back to the 90s, we had to replace R22 with a zero ozone depletion refrigerant. And we probably would have and should have just gone to use R32 at that point in time. We had R32 available, if not for the fact that it was flammable, okay? Because it was flammable, the industry wasn't ready to accept a flammable refrigerant. You know, like let's blend R32 with the fire retardant. That's R125. So that's actually where 410A came from back in the 90s. We blended R32 50% and then 50% fire retardant, so that blended refrigerant is no longer flammable, okay? At that point in time, global warming potential was not a concern. It's nothing we were thinking about. Today, as we address global warming potential, we're trying to drive down the GWP values of these refrigerants. There is no current chemical technology where we can do that without having to trade off and accept that low level of flammability. So R32 now becomes a very viable refrigerant in and of itself. There are some manufacturers that have chosen to use R32 as their air conditioning refrigerant. As a refrigerant manufacturer, we looked at R32 and said, hey, if we blend this with 1,2,3,4-YF, we can drive the global warming potential even lower, right? That's where 454B comes from. Many manufacturers have chosen 454B as the air conditioning refrigerant moving forward. So, and I tell contractors this all the time, there's going to be two different refrigerants moving forward. That's just the way that the manufacturers, you know, chose to go. Both of those refrigerants are below the required 700 GWP that the EPA has put out there. So the industry is just going to have to get used to using two separate new refrigerants moving forward on the air conditioning side of things. Let's go to the next slide. Let's talk about storage, right? This is where I mentioned the codes and standards are being changed, right? With the old codes and standards, before they're adopted by the states, the maximum amount of A2L refrigerants that you can store in a warehouse, 150 pounds. And if there's a sprinkler system, you can double that to 300 pounds. If we go to the next slide, I pulled this off the AHRI website. This is assuming the new codes and standards are adopted that address the level of flammability. That 150 pounds now becomes 20,000 pounds. And if there's a sprinkler system, you can double that to 40,000 pounds. So that's why it's really imperative that the codes and standards were rewritten to address levels of flammability. We can safely handle, mildly flammable refrigerants at greater quantities than we could before. So moving on, I like to talk to contractors, safety, installation, service, right? How are we using A2L refrigerants differently? On the next slide, I talk about refrigerants are considered to be materials of the trade by the Department of Transportation. So you can put an A2L flammable refrigerant in the back of a service van. You've got acetylene tanks, you have other flammable materials that can go in a service van. So long as you have 440 pounds or less refrigerant, you don't have to do anything. You don't have to put a placard for hazmats. You don't have to put a placard for flammability. The Department of Transportation considers refrigerant to be a tool of the trade. It's no different than having wrenches in there, 440 pounds or less. Next slide. On the previous slide, there was a picture of a rack with cylinders put in there horizontally. And I had a lot of contractors over the last couple of years ask, can I still use my horizontal racks? The answer had been no. About a year and a half ago, we got a special permit from the Department of Transportation that allows for A2L refrigerants to be stored or transported in the horizontal position. So I had a distributor ask me for a copy of that permit. When I went to the Department of Transportation website, there was about a dozen different companies that have piggybacked off that same permit. So just about anybody's brand of A2L refrigerant that's on the market is going to fall under this DOT special permit. No problem transporting those in a horizontal position. Next slide. A2L refrigerants are not meant to be retrofit refrigerants, right? So if you have a 410A system out there, you're not going to retrofit an A2L refrigerant into that system. It won't have the safeties for the flammability. Just keep using 410A. And when I'm in front of contractors, I tell them, if you learn nothing today, learn that 410A systems are going to continue to use 410A. The new lower GWP refrigerants are going to go in equipment that's specifically designed for it. Moving on. We'll skip this one. I'm running short on time. This only applies in areas where it's really hot and the pressures get too high on a cylinder. We had a burst disc on those cylinders before. With the A2L refrigerants, we've replaced that burst disc with the reseatable pressure disc, so we won't lose an entire charge. That disc will just pop open a little bit, relieve the pressure, and then reseat itself. So you'll lose very minimal refrigerant. Next slide. The cylinder differences that we're going to see from our HFC refrigerants to the A2Ls, there's going to be a red stripe around it. That's a visual indication that there's a flammable refrigerant inside. But more importantly, the valves are going to be opposite threaded connections. They're going to be left-handed threaded valves. And the first time you do a job with an A2L refrigerant, make sure you get an adapter that's going to be able to go on that left-handed threaded valve. You can use your standard hoses, or make sure you purchase hoses that have the left-handed threads on them. Next slide. This is what I tell contractors. This is a very easy transition, right? If you're following best practices today with your HFC refrigerants, you're good to go with A2L refrigerants. And the only three areas that may be different: purge your circuits with nitrogen, evacuate your circuits, leak and pressure test your system. These are things that all the good contractors are already doing anyway. For contractors that are taking shortcuts, you won't be able to do that anymore with the A2L refrigerants. Next. Equipment. Make sure you're purchasing A2L compatible gear for your jobs. On the upper right here, there's electronic gauges. Those, if they don't have the new refrigerants programmed in, it's a software update, a firmware update. No big deal. You can modify those. Next. Vacuum pumps, right? We got to have A2L compatible vacuum pumps. Those are the brushless motors. Most of the vacuum pumps were already being manufactured with brushless motors. The new ones are all redesigned now to have brushless motors. Just be cognizant that when you're working on a job, you're using A2L compatible gear to work on the job. So next. Cool.
Gone.
That's it. So thank you.
Thanks so much, John. And we are now handing things over to Ben.
Thank you, Tristan.
Mic
Thank you,
off.
John. So I'm going to discuss the codes and standards and kind of the status of those and how those are going to impact building design using these new refrigerants going forward. So this map is intended to show the status of both codes and legislation allowing these new A2L refrigerants in various states. This map is slightly out of date, but the good news on that, if we go to the next slide, so AHRI maintains an interactive map of the status of various states. So if you're working in a new jurisdiction or want to get up to speed in your current jurisdiction, you can go to their website and it will tell you what the overarching legislation and codes are. So in general, you can see for the state of Oregon, where I'm located, and this is going to be true essentially everywhere, the primary referenced codes are ASHRAE 15 and 34, which generally come packaged. So 15 is the safety standard, and then 34 provides the designations for the different refrigerants. And both the International Mechanical Code and the Uniform Mechanical Code reference ASHRAE 15 and 34. So in general, you'll be in good shape if you understand those codes. So go ahead and go to the next slide, Tristan. So within ASHRAE 15, with the A2L refrigerants, there are going to be new requirements that are going to have some pretty major impact on design, particularly of VRF systems. For starters, the concentration limits are generally lower for A2L refrigerants, and that is due to the fact that now, in addition to the toxicity and oxygen deprivation limits that are taken into account, we also need to look at the flammability limits, and the concentration limit on that front is 25% of the lower flammability limit. So in general, that is going to be the lowest limit for these A2L refrigerants. Here's an example comparing R32 to R410A, where you can see it's about 20% or less of the allowed concentration limit, and 454B is similar. So when it comes to a practical design sense, that means that you're going to need more independent systems with smaller charges to serve the same areas, and this comes into play primarily. I've seen a lot of VRF systems installed in multifamily housing and hotel motel applications. So now these systems are going to need to be split up further, which means more piping potentially and smaller systems. Next slide. So there are some additional mitigation systems when you go over those concentration limits. And this chart is, you can kind of ignore the numbers here, but just showing the general principles. In area A, you're under the limit for regulation in general, so that is 6.6 pounds of refrigerant charge for A2L. You don't need to be concerned with any additional mitigation. Area B is your as your smallest confined space or individual space dictates that you're over or under that concentration limit. As long as you're within that concentration limit, then there's still no requirement for additional mitigation. Once you start exceeding that limit, there are a couple of other thresholds. And in area C and area D, area E, all of those in general are going to require refrigerant detection. And then additional mitigation in terms of ventilation or shut off when that detection is set off. So again, getting back to what that means for design, if you're over that limit and you want to use these systems, you're going to need to add refrigerant detection at additional cost and additional controls. And next slide. So there are some additional requirements for piping as well. I don't have a slide for it, but where A2L refrigerant piping is run in stud cavities and other similar areas, there's a requirement to protect it with steel plating. And also there's a ventilation requirement. So for rated shafts. So anytime you're penetrating 2 or more floor ceiling assemblies or connecting more than 3 or more floors, you know, similar to other designs, you're going to need to put these pipes in a rated shaft, and that shaft will have to be either mechanically or naturally ventilated. So a couple of quick illustrations here. The mechanical ventilation has a minimum velocity based on the shaft size, and that table can be found in ASHRAE 15 or in the mechanical codes. And then that needs to be either always on or it needs to be triggered by a refrigerant detector placed wherever the refrigerant is going to concentrate. In general, these are heavier than air refrigerants, so that detector is going to be located at the bottom of the shaft. You can also naturally ventilate these shafts. The complication there from a design standpoint is that it requires a minimum 4-inch duct, conduit, or pipe, piped to the exterior of the building and sloped to the exterior of the building. So depending on where these shafts are located, that can be fairly complicated to coordinate. So there are other ways around this. You can place the pipes on the exterior of the building and you know, disguise them with louvers or some other component. I don't know if there are any architects on the call here, but I know how the architects I work with feel about that. But in general, this is going to add space requirements and coordination requirements to designs that use these refrigerants. And I believe that is the end of my slides.
Mic on.
Yeah, thank you very much, Ben, and thank you, everyone else. I'm just getting out of my full screen here, and we're gonna open it up for some discussion now. Helen, I think this one might be for you. Someone says they have a mini split from 2020 currently installed in my home, and I want to add a second one from a different room. A contractor told me if I wait until the change to new refrigerants, I'd have to replace the current one and add a new one because they aren't compatible. Is that true? If so, it seems like it would be an issue and would cause a lot of waste of older units that still function. And John, if anyone has thoughts on that, we'd love to get your input.
If I understand the question correctly, I think they're trying to understand what the trigger is, right? So for transition. So a split system, if in certain places, so in California and New York, if the outdoor unit is changed, it does trigger the requirement for the new lower GWP less than 700 refrigerant. There is a rule at the Department of Energy that would push this pretty much nationwide because of some energy efficiency penalties in the test procedure. It's not final yet and it's not in effect, but we are kind of waiting to hear about that from a light residential and commercial, residential and light commercial perspective. I think that repairs are still allowed. EPA does require manufacturers to label specified components, so that would be an indoor unit, an outdoor unit, or, a condenser, coil, et cetera, as a specified component. It would need to be labeled for repair only to continue to use 410A. So, today that repair is allowed for a 410A split system. Longer term, it may not be, and it won't be in California or New York if it's an outdoor unit only.
I do want to add one thing. There is a sell-through period for equipment, right? So the manufacturer had to stop making 410A equipment January 1st of this year, but the distributors still have a lot of stock of 410A equipment for single phase, for split systems, residential type equipment. There's a 1-year sell-through period. You can still purchase and install 410A equipment throughout this calendar year. For 3-phase equipment, packaged rooftop units, there's actually a 3-year sell-through period. So any of that's already been produced and in stock can legally be sold and installed for the next 3 years.
Yeah, thank you both for that. As older refrigerants are phased down and the use of A2L refrigerants increases, should the older refrigerants be reclaimed? And what is the current state of preparedness in the US for these old refrigerants?
I'll take that since I'm the refrigeration guy. Absolutely, they need to be reclaimed. Legally, you have to reclaim them, right? You can't just vent those refrigerants. They have to be reclaimed. There's a number of reclaimers. There's some large national reclaimers out there that a lot of the distributors have exchange programs. They'll take a reclaim cylinder that's full, give you an empty reclaim cylinder in exchange, and they're sending those off to the reclaimers to be reclaimed. In some markets, there's a cost for that. The contractors pay anywhere from $50 to $75 to do that exchange with the reclaim tank. In other markets, there's no cost, right? I was in Western Colorado last fall, and there's no charge to do that exchange program. Eventually, that refrigerant is going to have value to it. Contractors won't have to pay for that service, or they'll even get paid for that reclaimed refrigerant in the future. It's going to be required. California is one of those states. They started with any refrigerants above 2,200 GWP can't be sold in the state of California this year. So there's a big demand for those refrigerants, such as 404 and 507, to come back and get reclaimed and sold back into the marketplace. So.
I did want to add a little bit to that because it's a little bit confusing. So that there is a mandate under subsection H that no refrigerant can be vented. And so subsection 8, that's refrigerant management section of the AIM Act, does state that and requires recovery at the end of life. So recovery is when you take the refrigerant out of the equipment. Now, what's done after that? A lot of refrigerant in this country is recycled and maintained. The ownership is maintained by the equipment owner, and that's perfectly legal. It's allowed. You might hear RRR equipment where it's just recycled through equipment on site and then either put right back into the equipment or it's held in a cylinder on site. You can, it's voluntary. You can send refrigerant back to a reclaimer or it can be destroyed. But it does have to be recovered at the end of its life and then reclaim, recycle, destroy. That is the option. Those are the options on the table legally under subsection H. And as John noted, in California,
refrigerant over 2200 GWP. So if you think about R404A, only reclaimed refrigerant in bulk is allowed in the state. And then in New York, they've got the same mandate, but they have delayed that enforcement for a year. So we won't see enforcement until January 1st, 2026 in New York.
Yeah, thank you both. Will A2L refrigerants be well suited for air-to-water heat pumps installed to replace existing gas boilers, for example, for space heating? I understand that CO2 refrigerant systems seem to only perform well for domestic hot water heat pumps, and I have yet to see much info about systems with low GWP refrigerant that have good performance for air-to-water space heating.
Yeah, so I can actually take this one. So A2L refrigerants are well suited to air-to-water heat pumps. In fact, that larger equipment is ahead of the game when compared to the VRF and split systems. I've already installed our 454B air-to-water heat pumps over the last 2 years. So yeah, they'll perform pretty well, and they're getting better all the time in terms of like what heating water temperatures they can deliver. With regards to CO2, those actually do perform very well and can hit higher temperatures in a heating application too. The reason you don't see them very often is they're significantly more expensive than the other heat pumps. When I last priced some about a year ago, they were 4 to 5x the cost of a standard air and water heat pump.
Thanks. And how are the unconditioned vented shafts interior to the building for A2L transport treated by the Energy Code? Are these treated as additional exterior envelope surfaces in the energy modeling of a building?
So I can take this one too. The short answer is no, they are not treated as additional exterior surfaces, but as part of the design, you definitely need to consider if if it is truly an unconditioned shaft that you're moving outdoor air through. Depending on your climate and what the risks are there, you're going to want to consider how that's going to impact the adjacent spaces and your overall building conditioning. But they're not required to be treated as exterior envelope surfaces.
Yeah, I'll go ahead and insert my own follow-up question on that because I've been thinking about this a lot. Your diagram there showed two versions, right? A naturally ventilated shaft with the I think you said a 4-inch pipe going to the outside, and then a mechanically ventilated shaft with fresh air inserted at the top, and then a exhaust fan with a pipe going down to the bottom. In that second one, a mechanically ventilated shaft, and has your organization been thinking about that makeup air being conditioned to mitigate any energy impacts, potential condensation, like cold surfaces condensation risk potential, or would that be just outside air being inserted to that shaft?
Yeah, that's been the subject of some internal discussion here, to say the least. I think it really depends on your climate and how you're constructing that shaft. But I would anticipate in a lot of cases you're going to want to at least heat it for freeze protection, if nothing else.
Great, thanks. And then we've got another in the chat says, if we use air to water heat pumps, what is the pro for A2L versus natural refrigerants?
I think you're muted,
Maybe Tristan,
Helen.
I can start, and then maybe
Sure.
Ben and
Yep.
John can. Okay, so I think I think that there is work being done today around research around. So when we say natural refrigerants, I assume that somebody means propane or carbon dioxide. I'm guessing that's what that person means. There is work underway today that was started under the Department of Energy and actually through ASHRAE to evaluate propane, especially for heat pump use. You know, I don't know if people understand the process that standards bodies go through before they make modifications to standards. You know, a lot of the question is around, you know, the safety and equivalency of what society accepts from a safety perspective today. So you usually start with a risk assessment. So you look at the severity and the probability of an event happening, you know, any kind of leak or what have you that might go on. And as you can imagine, there was a question before John's segment around competent flammability, competent ignition sources for A2L refrigerants, which is an open flame. But as you can imagine, a competent ignition source for propane, there's many, many of them. And so you kind of have to assume that they'll be present. So you really have to think through, how do we not achieve the lower flammability limit for propane where an ignition source might be available. So I think where we are in the process is, I think that people have kind of sifted through, you know, first tier priorities for propane in different applications. And as the person said, you know, air to water, I think replacement for hydronic systems is a big area of interest, especially thinking, you know, could this be something that's placed outside of a building, you know, as an indirect system away from the occupied space. And so I think that is going to be the first area that's evaluated from this risk assessment perspective. And then once the risk assessment's done, you look at mitigation. You know, does something need to be done in case of a leak, right? So, you know, in the case of A2L refrigerants, sometimes there's air circulation required or other mitigating measures in place to avoid an ignition occurring. And then you would test that mitigation to make sure that it works well. So that work is underway, but it's not yet done. And I think, you know, I think there are many, many companies and, you know, organizations like ASHRAE, you know, kind of examining this question and trying to, along with some of the national labs and others, examining this question and trying to better understand, like, where, you know, from a safety perspective, this will work well.
Yeah, and piggybacking on that, I think, you know, from a design perspective, the advantage is that there are a lot of A2L manufacturers, or a lot of manufacturers that have A2L equipment that's similar, you know, to what people have been working with prior, and that's, like, you know, effectively off the shelf right now. Um, so that's the real advantage, and that's why it's less expensive than going to the CO2. CO2 is great in terms of it, especially if you're doing a retrofit for boilers and you need 180-degree water. But it is expensive for a reason. The operating pressures of CO2 equipment are much higher. Um, and you know, it's kind of niche manufacturers right now. I think as more people get into that game, that'll be a lot more viable, and we'll see a lot more of it.
Thanks. And then there's another question in the chat. For existing buildings in California, will the building engineering and facilities teams need to keep records and report to CARB when there has been changeouts of new cooling or heating equipment?
Sorry, I had a little trouble getting off mute, Tristan. So I don't know if people are aware of this. Under subsection H, the rule at the EPA, I'm going to start there, Tristan. Under subsection H at EPA, owners of equipment that contains more than 50 pounds of refrigerant are required to report on leaks, and there are requirements around equipment manufacturers reporting around refrigerant in equipment and how much is kind of brought into the U.S. or manufactured in the U.S. So there's there's a whole body of reporting that wasn't required until now, that's going to be in place in the coming years. In addition, in Washington State and California and New York, there are new requirements for building owners, or equipment owners, as this person has noted in the chat, around new equipment, and as well as to kind of help that understanding of where the installed bank of refrigerants are, and kind of what's happening there with them. So, Tristan, I think that we could have a whole session on reporting, and I bet people would appreciate it, because honestly, like, I think this is new, and I don't think it's well communicated yet within the states, the 3 states where they have that requirement, as well as federally. So happy to talk more offline if somebody has specific questions, but yeah, those reporting requirements are here. March actually is the first time in Washington State that requirement is in place, and people have to have their reporting in.
Thank you. And I noted that down, that refrigerant reporting requirements may be a good topic for a future webinar or conversation. Another question: per residential ASHRAE 15.2, shaft ventilation is required when there are joints in the piping within the shaft. Does that mean that we can omit the ventilation requirement if the design is based on continuous line sets within the shaft? My understanding is that the ventilated shaft requirements are coming from the IMC, but Ben, do you know more about that?
They're referenced in the IMC, but coming from ASHRAE 15. So to answer the question as best I can, that is how I would interpret that. But admittedly, I do not do a lot of residential work and haven't dug into that part of the code.
Okay, thank you. Lots of questions about air to water. What are the max output temps of typical A2L systems in air to water systems?
I've seen as high as 150 stated, and it's hard to answer this definitively without having the curves in front of me, because typically that varies, of course, based on outdoor air temperature. But I would say the max that you can count on at our typical design temperatures of like 25, 20 degrees here, you're looking at probably about 135 degrees.
Great, thank you. Well, I'm not seeing any more questions, and we're just about out of time. There has been a link posted in the chat for folks to give us feedback on today's session. I believe the slides and the recording will be sent out to everyone. So if you know folks who weren't able to join us today, or you want to revisit and to see any of that in more detail, please check that out. And I just really want to thank our attendees, Ben, John, Helen, not attendees, our panelists for getting together with us today. This was really great, and of course the attendees for being here with us.
Thank you, Tristan.